right, so 3.1, solving systems by graphing, should be review for you. You should have seen this in Algebra 1, maybe even in geometry. But we're going to solve systems of linear equations graphically. So basically, a system of equation is a set of two or more equations with the same variables, and the equations are all linear. Then you've got this system. So basically, we're going to be determining if a given point is a solution. So for example, two lines intersecting, this would be a solution for both. So that's what we're going to do first, just tell if it is a solution. So how can we tell? Well, if it's a solution, then evaluating both equations at a given x and y, the results should be equal. It should be true. The left side should equal the right side. So let's go ahead and take a look at this first one. We have a point 1, 3. So x is 1, y is 3. If you're one that struggles on where to put things, maybe using a highlighter might help you. So if you want to highlight the 1, and that's going to go in for the x's, and then we have the y is 3. So we're going to highlight the y, that same color. So let's go ahead and make sure everything gets put in its right spot. I'm going to go ahead and do the top equation first. 1 minus 3 times 3, does that equal negative 8? So let's simplify. 1 minus 9. Man, I cannot write today. It happens. My handy dandy eraser there. So 1 minus 9, does that equal negative 8? Yes. So this one works. Now let's try it in the second one. So we have 3 times x plus 3 times y. Does that equal 9? So 3 plus 9 is 12, and 12 does not equal 9. So no, this one is a no. And it's a no because even though it works in this one, it has to work in both for it to be a solution. So let's try another one together, and then I'll have you try the third one on your own. So x and y, and again, you can highlight if you need to. For the first one, negative 4 plus 6, does that equal 4 times 1/2? So this is my question mark of whether or not it's actually equal. So this is 2, and does that equal what's 4, half of 4? 2. Yes, that works. All right, so let's try it again for the second one. 2 times x plus 8 times y, does that equal 1? Well, half of 4, that would be a negative 2. 2 times 4, my bad. That would be negative 8. I'm already getting ahead of myself. Half of 8 would be 4. Does that equal 1? No. Negative 4 does not equal 1. So this one, again, is a no. So try that last one, number 3, on your own, and check when you're ready. And for that last one, you should have gotten a yes. It works in both, so it's a yes. All right, let's take a look at the next page. So when it comes to classifying the types of systems, we have basically 3 types. We have no solution, one solution, and infinitely many. No solutions are going to be called inconsistent. And those that have solutions are called consistent. And you've probably heard those words used before. But then, if it is consistent, we can also classify it as either dependent or independent. So independent is like 2 separate lines, parallel, that never intersect. Lines that never intersect. So add that little never in there because that is what parallel lines are. And then dependent is going to be the exact same line. So one line lying directly above the other line on top, and you can't even really tell that there's 2 lines. So independent, kind of separate, dependent, same line. So let's take a look at it kind of in picture format. The inconsistent, so the two parallel, the independent, or sorry, this is lines that intersect. They're considered independent as well. So these are two separate things. Parallel lines, those are the ones that never intersect. But then we also have lines that do intersect that are considered independent as well. So you can kind of see this one would be independent and this one would be independent. But this one is inconsistent and these two are both consistent. So let's take a look kind of classifying these. Well, we've got this one touching at one point, so that means we do have a solution. We've got one right there where they're touching. So one solution. This one never touching, so there's never a solution or no solution. And then this one, it looks like there's only one line, but really it's on top of the other line, so it's an infinite number of solutions. And then let's practice writing, well, which one is inconsistent? The one that's parallel. And so the ones that actually have solutions, those are consistent. And then the one that is, which one's independent and dependent? Well, those that are kind of separate are independent. So this one, independent, you can kind of see two separate lines. Dependent. And this one would be independent. And this one, though, looks like it's the same line, so that one is going to be dependent. And you'll get the hang of it with some practice. All right, so the next page, we're going to kind of practice, and there's a flow chart to kind of help guide you. So we're going to rearrange each equation first into slope-intercept form, and then we'll look to see whether the slope's the same or different and kind of follow our chart. So for these first few, let's go ahead and get our y alone. So number one, we would subtract 2x. And if you kind of want to put it under there, I'm going to go out to the side here. So we've got y equals negative 2x plus 3. And then for the next one, down below here, let's subtract 9. And then divide by negative 3 on every single thing. So it's negative 2x plus 3 equaling y. So seeing how this one has the same slope, we're going to go up to our flow chart and find same slope, and then we look at our y-intercepts. Oh, they have the same y-intercept too. So that means that it is consistent and dependent because it's the same line. And I'm just going to go ahead and write both those words. There. All right, let's do one more together and then I'll have you try the other two. So for this one, to get y alone, I'm going to subtract 3x from both sides. So y equals negative 3x plus 3 for this one. And then for the bottom one, to get y alone, just subtract 2. Y equals negative 3x minus 2. So see how these have the same slope, but they have different y-intercepts. So up here, same slope, but then we're going to go to different, so inconsistent, dependent. Because these are parallel. Sorry, independent. Because they're two separate lines and they're never going to touch. Try those last 2, 3, and 4 on your own. Make sure to get y alone first, then follow that flow chart and check when you're ready. All right, so let's see how you did. Pause if you need a little more time to look that over. And make sure to note any questions you have over whether it be changing them or whether it be the correct answer. All right, the last thing we're going to do is graph to solve, and this is kind of my favorite because I feel like it's the easiest. We're going to graph both these lines, and if they touch, that's going to be our point. If they never touch, then no solution. Or if it's the same line, then it's that infinite number. So let's take a look at this first one. Let's start at -3, always on the y-axis, with a slope of 2/5. So rise 2, run 3. Up 2, right 3. And let's continue. Up 1, 2, right 1, 2, 3. Up 1, 2, right 1, 2, 3. It really helps to have a lot more than just 2 points. That way you get a consistent line that you can draw, because we really want it to be as accurate as possible. Otherwise, you're not going to match up at a direct point, and that point is your answer. So if you don't match up at a direct point, then you're not going to get the correct answer. So this is very important to put as many dots as you can and use a straight edge, again, as straight as possible. See how I went up 2 and over 3? You could continue that same pattern just going the other way. Over 3, down 2, over 3, down 2, to get as many points on that line as you can. Graphing the second line, start at -2, move up 1 over 1. When there's nothing here, we know it's a 1, and then 1 over 1 would be our slope. So up 1 over 1, up 1 over 1. Again, continue this line until you've got enough points, which is almost never enough. And now you can see that you are intersecting right there. And that coordinate is -3, -5. And could you check your answer? Yeah, you could plug this in just like we did on our first example and see if it works in both, which it should. All right, let's try one more together and then I'll let you do the last one. Well, before we can do this one though, we need it to be in slope-intercept form. So let's subtract x. We have -y equals -x plus 2, divide by -1. Y equals x minus 2 is 1 equation. And then over here, add 3x. Again, our goal is to get y alone. And divide by 2. Make sure to divide every single thing. So y equals 3/2 x minus 1. All right, let's graph it. Starting with the first one, go to -2, put a dot, always on the y-axis. Again, 1 over 1 for the slope here. Up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Continue until you've got lots and lots and lots and lots and lots of dots so that it is accurate. Again, even just the slightest bit off and you're not going to be able to tell where it's truly intersecting. And then our second line, start at -1, move up 1, 2, 3 over 2, up 1, 2, 3 over 2, up 1, 2, 3 over 2, and continue the other direction. So down 1, 2, 3, left 2. Oh, and we can kind of see on that one where we touch already, which is nice. Okay, let's circle that point where they're touching. So there it is. We're at -2, -4. And make sure to write it as an ordered pair, and that is your solution. Try number 3 on your own. Pause and check when you're ready. And this one should be parallel. So this one should actually be no solution because they're never going to touch. And remember, hopefully you changed those and check your graphs. All right, make sure to write any questions that you have and be sure to ask those in class.